Okay, we begin our next major unit here after the last exam on waves and sound. That leads directly into a description of light. Specifically here, we now begin to take a look at optics. Light is a wave. Okay, now, so recall some of the basic properties associated with mechanical waves. Mechanical waves, for example, reflect, they refract or transmit, they diffract, which I'll get to in this unit a little bit later on, and they also interfere. So recall some of the basic properties of mechanical waves. Reflection, refraction, okay, what's called diffraction, which, as I said, I'll get to a little bit later on, and interference. Now, if light is a wave, it should also have these properties as well. What I want you to do at this point is pause the lecture and then take a look at the simple demonstration videos that I have posted for you on refraction, reflection, and then also what is called Young's experiment. Young's experiment is the definitive experiment or demonstration that shows that light is a wave. It shows the interference of light. So go ahead and take a look at those demonstration videos now. Okay, now that you've looked at those demonstration videos here, let me now go through an explanation of Young's experiment. As I said in that video, Young's experiment, the definitive demonstration that light is a wave, is designed to measure the wavelength of light. Okay, so Young's experiment. We're in the early 19th century. It's a demonstration of the interference of light. And it is kind of the definitive demonstration that light is a wave. Demonstrates that light is a wave. Okay, so the experiment itself is designed to measure the wavelength of light. And it's a situation that we have seen before. It's a situation involving two-source interference, which was briefly covered in the last unit in the ripple tank. So at this point, what I want you to do is pause the lecture and then take a look at the screencast video that I've posted for you showing two-source interference, once again, in the ripple tank. But in this case, what I do in that demonstration of screencast is I produce the interference pattern by taking plane waves and having those plane waves incident upon two very closely spaced holes referred to as slits. So go ahead and take a look at that screencast now. Okay, now that you've seen that screencast, here is then ultimately how the pattern itself is produced. Okay, so first of all, the experiment itself is drawn out in the following way, and we also have some definitions associated with it. Okay, first of all, the vertical slits themselves are usually drawn like this. So here's one vertical slit in this direction, here's the other in this direction. Okay, they're separated by a distance here. This distance is referred to as small d. Okay, now exactly what is the distance small d? For example, is it from here to here, or is it from here to here? Well, one of the things that we're ignoring for simplicity here in our description of Young's experiment is the size of each individual slit itself. We're going to consider each individual slit to be a point. So then therefore the distance d is just the difference, or the distance rather, from one point to the other. Okay, D is an experimental control. As you saw in my demonstration video of Young's experiment, the spacing between the two slits themselves is extremely small. Okay, and then we draw an axis like so that is perpendicular to the slits. And then right here is what is generically referred to as the screen. Okay, the screen is basically the whiteboard where you actually saw the actual demonstration itself, where you saw the interference pattern. Okay, the distance then from the slits to the screen is usually referred to as capital L. Capital L is the distance basically from one side of the room to the other here in the demonstration that you saw. L is gigantic compared to small d. That's very important later on. Okay, and then the pattern itself here forms on the screen. So for example, you see this bright spot here right in the center of the pattern, this bright fringe. This is referred to as the central maximum. And then you see the alternating pattern of bright and dark fringes, antinodes and nodes, symmetrically on either side of the central maximum. So the next bright fringe, for example, is here and here. Next one after that is here and here. And then eventually the pattern itself dims out as you begin to move to the sides. Okay, let's pick a particular point on the screen. For example, like so. This is usually referred to as point P. And then we have a distance here on the screen from that point P to the center of the central maximum. That distance right here is referred to as Y. Y is something that can be easily measured. L and D are experimental controls. Okay, we're also going to define an angle here on the diagram as well. I'm going to do so by drawing a line here from the center of the two slits to that point P on the screen itself. This angle right here is referred to as theta. Theta is really tiny. You'll see this numerically in my example, and we'll also use it later on to make a small angle approximation. But the angle theta is tiny. Okay, notice on the diagram, however, that the tangent of theta is equal to y over L. Okay, now ultimately here's how the pattern itself gets produced. Let me do some erasing here. So this is basically what you saw in the screencast demonstration here using the Ripple Tank applet. All right, so once again, right here are the two slits, axis and screen and so forth. And now think of the slits here as source 1 and source 2. Okay, and then we assume that we have incident plane waves of light that are incident upon the two slits. How do you produce those plane waves of light? Well, we'll get to that a little bit later on by using Huygens principle, which was also briefly touched upon in the last unit. So right here from the laser, for example, are plane waves of light that are an incident here upon the two slits. And then each individual slit behaves as a point source of circular wavelets, once again by using Huygens principle. So then therefore propagating outwards from source number 1, this hole if you will, are circular light waves like so. Propagating outwards here from hole number 2, source 2, are circular light waves like so. And then the circular light waves here, they begin to encounter one another, and then therefore they begin to interfere. The actual interference pattern itself is present here in the room. You can see this, for example, in the Ripple Tank screencast that I've posted for you. But when you actually look at the pattern itself, you don't see the pattern in the room. The reason for that essentially is twofold. Number one, the dimness of the laser light here in the room, well, it's extremely dim. So then therefore, in order to actually see the red light here in the room itself, what I would have to do is like rain chalk dust from the ceiling or something like that, and I'm certainly not going to do that. In addition to that, you can see the individual waves themselves, of course, when you take a look at the Ripple Tank interference pattern, and that's because the speed of water waves, for example, is quite small. Here in this case, we're talking about the speed of light, which is 3 times 10 to the 8th meters per second. That's a very important number, by the way, later on in this class. But for now, the reason why you can't see the actual waves themselves here in the room is because they're just propagating too quickly. But basically what you then see are all the waves effect, if you will, as they pile up on each other here on the screen, resulting in the alternating pattern of bright and dark fringes. So it's the exact same interference pattern as the ripple tank experiment. It's just in this case, you only see the interference pattern itself on the screen. That's how it gets produced.